Hey there, everyone. My name is Ryan Schul. Welcome to my channel. So, in the topic today, I want to take a look at how we can optimize EV charger placement. And we're going to focus on a couple of things. Traffic patterns, of course, right? If you have higher traffic flow, it would make sense to put EV charging sites there, right? As opposed to low traffic flow. And dwell time analytics. So, this is more like how long are people going to hang out, and are there things for people to do for 15 or 20 minutes or whatever while their car is charging, right? If it takes a couple of minutes, you probably don't need some type of, what would it be? Not entertainment, but just something to do with your idle time. If there's nothing around and literally you're just in a barren desert, it's going to be a long 20 minutes or 30 minutes or whatever to recharge the car. So that's going to be the review today. We'll focus on traffic, dwell time, of course, right? Candidates, and look at different cities, right? Different metro regions across the United States, and make sure to get land-only polygons, okay? Because with polygons, when these things are plotted, if you don't control for it, you can actually get some that go into a body of water, a lake, the ocean, a river. Obviously, we can't put recharging stations in the middle of a river. It doesn't make sense, right? So we have to add some constraints and control for that. So we download city boundary information extract road nodes from OpenStreetMap, right? So we're getting this data dynamically, and it's all maintained in a very clean, structured form. And we're going to look at demand points using synthetic, randomly sampled points within the city's land polygon. I'm going to show you how to do that. And now, ideally, you would want to collect actual information that pertains to all of these different topics that we're going to look at. But number one, there's no free source for all of these. It's scattered all over the place, right? And I mean, it's probably going to take an arm and a leg if you can even find this data. A lot of this data doesn't really exist in a clean, structured form, but I'm going to show you how we can do this in a pretty streamlined fashion. And then I think a good next step would be to, put in a little more effort and do some labor and try to find some of these data points to make it a little bit more realistic. But this structured script that I came up with should do a pretty decent job. But again, some of this is real actual data that exists today. Some of this is realistic assumptions. I think it works good. The next level to take this up a notch would be to get all this data, but that's a big ask. That's a big ask. And there's nothing out there for free that's going to have all that for us, right? So we're going to look at a few different functions I created here. We are going to draw up random data points within polygons and use the demand to discover candidates that would be a good location for an EV charging station. We're going to download road networks within the polygon, which is a mathematical shape of a city, where you're going to orchestrate data preparation to get city boundaries, right? And we're going to say within the boundary of the city, there's probably multiple ways to do this, and you can probably combine data. I did see one example where we can combine data from all of New York City region, which is 5 boroughs. So it includes Manhattan, Brooklyn, Queens, Staten Island, and Bronx. But in most cases, I don't think you have to combine all that data together. And then because we just get the top 10, it's really going to be scattered all over the place. The optimal points to place an EV charging station, right, when you're doing the install, I don't think that makes a whole lot of sense. I think you have to focus on one specific region and analyze that rather than just the big picture, right? If you try to look for the top 10 locations across New York State, you can do that, but that might not make a whole lot of sense, right? You might have a couple in New York City region, a few upstate. I think it makes more sense to focus the analysis and just look at these microcosms, right? So we're going to compute an efficient matrix using Euclidean distances. So you see this all the time in the clustering world, right? We're using Euclidean Manhattan distance, and there's another, I think, that combines those two together. I forgot the terminology now, but Euclidean distance is very common. Manhattan distance is used sometimes as well. The difference being Euclidean is a straight line, and Manhattan would follow sort of like the grid line pattern of New York City. So the last thing here I'll mention is that we run iterations, right, and try to optimize the way that we pick the best point for these sites, again, based on traffic patterns and dwell time for people that will visit these EV sites and take probably 20 to 30 minutes to charge their vehicle. So here's the setup. I've got a couple libraries I'm importing. I want to look at Manhattan, focus on that. Pretty much everybody knows Manhattan. You know the shape, you know the boundaries of the city because it's completely surrounded by water. So you know the upper, lower, east side, west side, sort of like boundaries for Manhattan. We know what that looks like. We're pretty comfortable with that. So I think this is a good first step. And we can circle back and look at a couple other metro areas after that. So I'm going to go ahead and get the land polygons. Again, we want natural boundaries for all of these different cities, right? So if Manhattan or Queens or Brooklyn or whatever, it's cut off at a certain point, and then you're going into the next county over, like Nassau County or Suffolk County, if you're traveling from Queens, from west to east, then we want those natural boundaries, right? Anything that's in water, we want to kind of erase those or cut those out because we can't build a charging station on top of water. And anything that is like not a legitimate spot to build is going to be handled as well, okay? And there's other things too, like zoning ordinances. I'm not even going to get into that. That can get pretty complicated, right? And again, you would have to have data to support your claims. Is this zoned for an EV charging station or is it not? I don't have this data, so I can't do the analysis. But to make this very realistically, to execute very realistically, I think you would want to go ahead and do that next step to make sure this is truly optimized. In the example today, I'm going to show you a very realistic, very close approximation, but this is not going to be like 100% guaranteed to be the optimal solution, right? A lot of times when we do optimization, we can optimize with amazing precision, but if some of the data is just missing, or you have to kind of cut corners because you can't afford to buy the data, or you just can't find it anywhere, you do the best you can do. I think the final product here looks pretty nice. It's pretty impressive, but is this absolutely perfect? No, it's not. Okay. So just to get that out of the way, we're looking at polygons, the overall areas, the probabilities here, and running a quick loop to go ahead and put random points within this polygon and test how these points are located around this geographical region, and how do we optimize the install for these EV charging stations, right? So we get a bunch of candidates and say, okay, this could be a good candidate. Maybe this one is not. We'll kick that out. Maybe it's just too far away from a major intersection, right? If you have a major intersection, maybe I'm just thinking like with 3 or 4 lanes going horizontal and vertical, maybe it makes sense to put an EV station there because you're going to get a lot of traffic going through that spot, right? So we're looking for these locations where we have the volume of traffic, where we have the demand, right? And we're going to create our own supply. And that's the whole point here. And try to do it in an optimized fashion, okay? So that is the goal here. We're going to work heavily with latitude and longitude coordinates, right, for some of these optimization plotting tasks, and just to visually render images on a chart where these things sit and what they look like, okay? So we're going to assign weights, right? That's what this function does. We're assigning weights to understand the overall demand, what is going to be the volume of traffic going through any particular road or causeway around Manhattan. And then we have to go ahead and do the optimization as well. And again, look at pairwise distances. So this is where the Euclidean calculations kick into play, right? So Euclidean, again, is looking for the shortest distance between 2 points, but also it can't just be randomly just going in a straight line. Maybe the road doesn't go in a straight line. Maybe the road curves a little bit, right? So you have to take this into consideration too. If the road just doesn't go perfectly straight and you have to deviate and take a little turn, you have to follow the road, right? You have to follow where it goes. But given these constraints and the assumptions I described above, we're trying to optimize to the greatest extent, right? So the algorithm is greedy. It's going to look for the best possible outcome, okay? And we're going to plot everything on a Folium map. You'll see what that looks like in just a moment here. These Folium maps are pretty cool. I've used this pretty extensively in the past in different places I've worked. And in my channel, you can find several examples of using Folium maps to do your plotting. I like these things a lot. Totally free, and it covers, I think, as far as I know, like most major roads, probably all the major roads, a lot of the smaller roads, secondary roads, and maybe even tertiary roads too. I think the coverage is pretty decent. I don't think I've ever looked for something on a Folium map, but I haven't been able to find it. So there are a couple caveats or gotchas here. You have to go ahead and feed this into a Folium map. If I show you just a basic example here, it's a little bit complicated to get it really to do really impressive things. Maps, but just to do pretty straightforward and simple things is actually pretty easy, right? So here's the Folium documentation. You can get a ton of stuff over here. I guess maybe this looks like it changed a little bit. Is this the actual documentation? Yeah, this is some of it. Okay, so here's the basic Folium map view. Here we see Portland, Oregon. I used to work here a long time ago, so that just offhand looks pretty detailed and pretty accurate. I don't remember all the streets and the twists and the turns and curves, but this looks pretty accurate. Just first pass here. What else? So we have Portland, Vancouver. I think that is Washington, right? When you go over the river there, you're in Washington. And they have some more detailed maps here. This is what? Mount Hood. Okay, so that's also around Portland. So the guy who put this together, or the girl, probably lives somewhere around Portland, I'm guessing. So there's some basic documentation there. It looks like you can find a little bit more over here. This one might be new. I don't know if I've seen this one yet. Okay. I think this is relatively new. I don't think I've come across it, but that's fine. So they give you some basic setups, and you can start to see how you take all these different elements from data frame, from different lat long coordinates on your data frame, and you can build different layers and feed all of this into your data frame and then render the map, and it will show you all the details of the lat long coordinates right here. Okay, and it'll plot everything for you automatically and almost instantaneously, right? And if you need help, there's GeoPandas, there's reverse geoplotting, there's what is it called, forward geoplotting, or maybe just geoplot and then reverse geoplot. So you can actually get lat long coordinates from the address, from the street address, or get the street address from the lat long coordinates. Okay, so it goes both ways. Okay, so that is just a little intro on Folium maps. So we go ahead and load in all of the different details into the different layers of the map, and then we plot the map down here, or return the interaction from that map. And I'm also using Plotly to create the geometric patterns for all of these boundaries of different cities that we're going to feed into the process here. So here is the main part of the function that calls all of these UDFs that I just described, the user-defined functions. We take everything, feed it into Plotly, feed it into Folium, do all the calculations, all the optimization and everything, and find out, where's the most dense traffic area locations, and what kind of dwell time analytics can we expect here, okay? So here's the final result. We have the lat long coordinates and the approximate gain. Let's just look at the map real quick over here. I think I called this wrong thing, approximate. Okay, the approximate gain is basically the marginal covered demand with each selected site and how much contributes to the moment that was picked by the greedy algorithm. Okay, so it's a little bit complex, but it's not too bad. We've got lots of demand dots. Okay, so as a demand here is, and over here, and over here, and over here. So we want to understand where are these demand dots relative to everything else, and are the candidate sites already covered? Is there already an EV station close by? Yes or no. If there is, then we don't need another one, probably, unless maybe there's just one at that spot. Maybe adding a couple more would make sense. But if you already have 10 or 12 chargers, does it make sense to put one across the street? Probably not, right? So we have to understand the coverage, what's pre-existing, and then how can we add value by installing new EV charging stations without cannibalizing the ones that already exist, okay? So what else? If a site reaches an average importance, the marginal gain increases, okay? So you're looking for this algorithm to go ahead and do all these calculations and checking based on the Euclidean distance and the optimization process itself, and how much are you gaining by adding EV stations here. If you're not gaining and you're kind of losing or just going horizontal or going down, right? If you're losing marginal gain, then don't put the site there. It just doesn't make any sense. Let me go ahead and close this thing, open the output, and I can show you what it looks like. It's pretty nice. So I put this into an HTML file. These HTML files are very, I wouldn't say powerful, I almost said powerful, but very interactive, very dynamic. You can see the heat map here. So the darker the blue, the more high density traffic areas, right? So it makes sense to put these EV chargers here unless there's already existing chargers, right? Or unless maybe the population density just isn't great enough to warrant that kind of install. So we always get the top 10. You can see 6 are kind of towards the top down here. 4 more are kind of in Midtown or something. I guess this is Midtown. This is chosen number 10. The lat is 47.6 and the long is 73.99. So if we go back over here, number 10 shows up over here. We have to really look at the end numbers, right? Because that gives you all the precision. So 4399, 1751. Get back over here. So 1751, 4399. So that is fine. Let's see what else we got here. It's number 8. Let me look for number 1 if I can find that. It shouldn't be too hard here. Number 1. Okay, we end up with 2662 0078. 0078, that's what we see there at 2662. So I think this is working. I think the plot works, and the approximate gain, again, we're looking for the biggest gain based on traffic patterns, dwell times, right? What are people going to do while they're waiting for the car to be charged up? So those are the kind of criteria here, and this plot is pretty interactive. So so we can click on this and change the view and the appearance just a bit. So this is the boundary of New York City itself, right? You can see slightly, this used to be called dancing ants. I don't know if this will do that or not. Demand heat, right? This is the heat map itself. We have the candidates. These are all the potential locations to install EV charging stations, remember? But again, if it's not really high traffic area or there's not a lot of dwell time, then we're not going to do it. So the candidates are great. We need the candidates, but we're trying to optimize where we're actually doing these installs, right? So if I go over here, we can see candidates again, and the optimal are the top 10. So let me go back here. Let me change this now. Let me make this Queens. I live in Queens, New York, so I'll change it to Queens. We'll take a look at that. I'm going to hit the pause button for just a minute. Okay, as I kick this off to run it, because it does take a few minutes on my machine to run, probably 5-6 minutes, give or take, I guess about 5 or 6. So you don't have to sit here and wait for this thing to run. I'm going to hit pause. I'll be back in a few minutes. Bye. Okay, so it looks like that has finished off. I have this download pointed to my desktop. I think I mentioned this before. I'll just take you through a couple of the parameters here. This is the city that we're searching for, the number of demand points. So this is 2,500 potential sites for installing these EV chargers. Number of candidates, we're going to pick a subset from the 2,500, 300, but from that, we're going to actually pick just the top 10, because I don't think we're going to be installing 300 different EV charging stations, at least in New York City. I've never seen that. That doesn't make any sense around here. Maybe some parts of the country have that, but certainly not New York. Number of sites is 10, and then the radius is the coverage in meters for the served demand. So I set that to 600 meters, okay? Because you could drive a little bit to get to a charging station, but you're probably not going to drive miles and miles and miles. So here it goes to my desktop. This is Queens, okay? So this is the neighborhood where I live. And we got the top 10 right here. These are the chosen sites. These are all the candidates comprehensively. This is the heated map, right? The heat map that we're working with, and the boundaries of Queens, right? So that's there, that's gone, there, gone. So hopefully that makes sense. I'm going to hit pause and look at just 2 more use cases. I'm going to look at Seattle and I think Chicago. I lived in Chicago for a little while, so I know that area too. We put Chicago, Illinois. Okay, and the output will go to the desktop. Okay, Control Enter to run. I'm going to hit the pause button. I'll be back in a few minutes. Bye. All right, this is good. This is good. Now it looks like the script has finished, and here's our map. We can zoom in on this. So like this one, this is just the pure Plotly map, but Plotly isn't really great at giving you all the details of all the streets. I mean, they do have I think they do have something in their code library that does allow for that, but I think like Folium is probably just a better option. So I want to look at both of these together, right, and overlay something on Folium and use Plotly in conjunction. Okay, so I think we can go over here and open our Chicago map. So let's see what we get. Okay, that pretty much looks like Chicago to me. We have some of the outlying neighborhoods here. Okay, so where's the heat map and the bubble over here? Just south of Evanston, right? So I think Northwestern University is located there, and you have all of the like Chicagoland south of that, right? So we have our top 10. This is all in red. These are the candidates that we're choosing, or chosen sites, right? And we have all of the heat over here, the boundary of the city of Chicago, and then all potential candidates right here. Okay, so I think that one worked out just fine. Let's look at one more example, and I think you get the picture at this point. One more example here, and I'll go over to Seattle. So that is all queued up, I believe. Yeah, Seattle. Okay, so let me hit Control Enter to run it. That thing's going. I'll hit the pause button, and I'll be back in a bit. Bye. Okay, we're looking at some good stuff here. This looks like generally a plot of the borders that outline the whole perimeter of Seattle. Now we're looking at Seattle, okay, but again, this is Plotly. This is good for some type of maps. It's not great for a lot of maps. They do have some. Let me take you through it just real quick here. I'll go off on a big tangent. Plotly. Python, yeah, Python. They do have a few that are not bad at all. Here's a couple examples over here. You can check that out. Chloropleth maps. This is sort of like the whole border with the interior of whatever object you're looking at. This could be counties around the United States or state shapes themselves. This is pretty pretty illuminative, like an insight, I think, on these are FIPS, these are county codes. But in terms of like Plotly street maps, let me see. I feel like I have seen something before. Oh, let's see over here. Map, tile map leaves in Python. What is that? Okay, yeah, they have some things. So there's a couple ways to solve the problem, right? Plotly or Folium. I'm going with Folium. I think that's a good option in this case. I could look into that Plotly thing a little bit later. So here's Seattle. Let's pull this up and see what we got here. Okay, so I think it's working. So we've got some good coverage here. This actually, this looks like water over here to me. It does go out into the water a little bit. I have to true that up a little bit because we can't have an EV station on water. And I thought I did account for that. I can look for that again. Try to circle back and get that fixed. I think I do see a mistake over here. This thing could be on the edge here. It was a dock or a pier. This one, like right here, does look suspicious because it looks like it's not on land, right? You're not going to have an EV station on a boat. So to look at that a little bit, but I think this is 99% of the way there. Could it be improved a tad? Yeah, probably. I think it's the borders of Seattle, the city of Seattle, go out into the water. But again, one of the constraints definitely should be land. It should be land-based. We can't build an EV station on a river or a lake or an ocean or something like that. It just doesn't make sense. So, you know what? I think I'm going to wrap it up here. I'm going to say this is 99% done. I'm going to circle back and see if I can fix up that code just a tad, just to make this a little tighter, a little more crisp. Because I think I do see a mistake here. Maybe there is an additional constraint I have to add. I have to do some research. But anyways, I think we covered the topic pretty fully. I'm going to download a copy of this code and upload the sample code when I upload the video a little bit later today. I'll take care of that. And that's it, guys. That's how to optimize EV charger placement using both traffic patterns and dwell time analytics. So hopefully that was insightful and informative. And that's it. Thanks for sticking through this thing to the end. Appreciate that. And I'll see you guys soon when I post the next video. Goodbye for now.